Hey there, 6th grade. In this video, we're going to be talking about accuracy and precision. So go ahead and read this scenario at the top with me as I read it aloud. It says, ancient Greeks used measurements taken during lunar eclipses to determine that the moon was 240,000 miles from Earth. And then in the year 1969, the distance was measured to be actually 221,463 miles. So notice that there is an obvious difference between these two measurements, and the reason is because as technology progressed, we got to the point where we could measure the distance from Earth to the moon with greater precision. That word precision refers to the level of detail that an instrument can measure. Now, when I say instrument, I'm talking about anything that will measure a unit. So you could be talking about a ruler, a compass, a protractor, a thermometer, a scale, okay? Anything that measures a unit of length or mass or volume or temperature would be considered an instrument. And the smaller the unit an instrument can measure, the more precise the measurement will be. For instance, if we were talking about a ruler that measured millimeters would have much greater precision than a ruler that only measures centimeters, and that's because millimeters have smaller units than centimeters. So the smaller the unit, the more precise the measurement, and that's what we're going to look at in examples 1 and 2. For each of those, you've been given 2 measurements, and you're going to choose the more precise of the 2. So number 1, we have 37 inches compared to 3 feet. In this case, 37 inches is more precise, and the reason is because inches is a smaller unit than feet. Okay, for number 2, we have 5 kilometers compared to 5.8 kilometers. In these 2 measurements, the units are the same, so we need to look at place value. In the first measurement, we're measuring to the nearest whole number, 5 kilometers. In the second measurement, we're measuring to the nearest tenth of a number, 5.8. Because tenths are smaller than ones or whole numbers, we would say that 5.8 kilometers is more precise. Okay, so when we're talking about measurements in the real world, no measurement is going to be exact. There's always going to be a way to get a little bit more precise with that measurement. For instance, if we're talking about the temperature outside, normally we round temperature to the nearest whole degree when we're talking about the outdoor temperature. You're not going to see a forecast on the news that says that the temperature will be 46.3 degrees outside. They'll say either 46 degrees or 47 degrees. Okay, so no measurement is exact. The exactness of the measurement is what's called as accuracy. And this discussion of accuracy brings us to what are known as significant digits. So when we're measuring a value, all of the digits that we know with certainty are called significant digits. So let me explain that with a scenario. Imagine we want to know the population of the state of Indiana. Well, in today's age, if I want to know a fact like that, I would just probably go to Google. So if I go to Google and type in population of Indiana, the first result I get is the following: 6.597 million. And so that's according to what I would assume is census data. Someone actually went through and calculated approximately how many people are in the state of Indiana. This number would be the same as 6,597,000. That's what 6.597 million is. And now let's talk about what this number really means. It's unlikely that there are exactly 6,597,000 people in the state of Indiana. It's possible that there could be 6,597,011. It's possible there could be 6,596,984. Okay, or a lot of other numbers that are really close to 6,597,000. What this number is saying is whoever surveyed and got this estimate is pretty sure that to the nearest 1,000 people, this number is accurate. Okay, it's not off by more than 1,000 people. Otherwise, they might have said 6,600,000. So these 3 zeros at the end of this whole number are what we call non-significant digits. Okay, those zeros are non-significant because what we're doing is we're rounding to the nearest 1,000 to give this estimation. So now that we've talked about what non-significant means, let's talk about what significant digits mean. And I have a table below here that explains the different scenarios where you have significant digits. First of all, anytime you have non-zero digits, digits that are anything but zero, those are considered significant. So in the number 45.7, none of these digits are zero, therefore each digit 4, 5, and 7 are what are called significant digits. So there are 3 significant digits in the number 45.7. 4 is 1, 5 is the second, and 7 is the third. Another example of significant digits are zeros that are between significant digits. So for example, in the number 78,002, we know that 7, 8, and 2 are significant because they're not zero. The zeros that are in between 8 and 2 would also be significant. So that means that there's a total of 5 significant digits in this number. Finally, zeros after the last non-zero digit and to the right of a decimal point are significant. So look at the number 0.0040. Any zero after the last non-zero digit would be significant as long as it's to the right of the decimal point. So these first 2 zeros here and here are not significant because they're not after a non-zero digit. But this 0 at the end is significant because it's after the 4. It's also to the right of the decimal, so that means that there are 2 significant digits in this number, the 4 and then the last 0. So what we're going to practice on the back side of your now are to determine the number of significant digits in each measurement. So in number 3, you have the measurement 120.1 miles. So let's go ahead and count the non-zero digits first. We have a 1, a 2, and a 1 here. So far, that's 3 significant digits. Now we need to look at the 0 and ask ourselves, is that 0 significant or not? Well, because it's between a 2 and a 1, it would be considered significant. So that means that there are 4 significant digits in this number. Okay, number 4, we have 0.0350 kilograms. Let's go ahead and start with non-zero digits. So we have a 3 and a 5. So far that's 2 significant digits. And now let's look at the digits that are 0. So we know that in order for a 0 to be significant, it has to be either between 2 significant digits, and we don't have that for this problem, or it has to be to the right of significant digits and to the right of the decimal point. Well, these first 2 zeros are not to the right of any significant digits. Okay, they're to the left. So those zeros there are not significant. But the 0 at the end is significant because it's to the right of 5 and it's to the right of the decimal point. So that means that there are the 2 plus the 1 0, so a total of 3 significant digits in that number. When you are adding and subtracting measurements, the answer should have the same number of digits to the right of the decimal point as the measurement with the least number of digits to the right of the decimal point. So let me explain what that means in example 5. We have the problem 45 miles minus 0.9 miles. And so not only are we going to subtract those two numbers, but we're going to practice using the correct number of significant digits in our final answer. So first of all, let's go ahead and do that subtraction problem. So it's 45 minus 0.9. So we know when we're subtracting decimals, we need to line up the decimal points. So this is 45.0 minus 0.9. I'll need to borrow from 5, so 10 minus 9 is 1, 4 minus 0 is 4, and then I bring down my last 4. So normally, to answer this problem, I would say that the answer is 44.1. But because we're subtracting measurements here and we have units, we need to give our answer with the correct number of significant digits. In this problem, our first number, 45, had 0 digits to the right of the decimal point. Okay, it was rounded to the nearest whole number. Our second number, 0.9, had 1 digit to the right of the decimal point. When we're giving our answer, like I said above, we need to give our answer so that it has the same number of digits to the right of the decimal point as the number with the least, or the least precise number. So we're going to use this number of digits to the right of our decimal, so 0 digits to the right of the decimal, and that means we're rounding this number 44.1 to the nearest whole. So 44.1, if we round that to the nearest whole number, that becomes just 44. So our answer to this problem is 44 miles. Okay, now let's look at an example when we're multiplying and dividing. When multiplying and dividing measurements, the answer must have the same number of significant digits as the measurement with the least number of significant digits. So in example 6, we're multiplying 32.8 meters times 1.5 meters. So let's first of all do that multiplication. So 8 times 5 is 40. 5 times 2 is 10, plus 4 is 14. 5 times 3 is 15, plus 1 is 16. And then in the second row, we'll add a 0, and now we'll multiply 1 times 8, 2 times 1, and 3 times 1. And remember, multiplying, I need to count the number of decimal places, so this becomes 49.20 would be my answer if I was just doing regular multiplication. But again, I'm multiplying two measurements. These both have units, so I need to use the correct number of significant digits. So you need to ask yourself, how many significant digits does 32.8 have? Well, 32.8 has 3 significant digits. How many significant digits does 1.5 have? 1.5 has 2 significant digits. So in our answer, 49.20, we need to round this so that it has the least number of significant digits between our two choices up here, which is 2. Okay, our answer needs to have 2 significant digits, and so we round this to the nearest whole number, and that would give us 49. 49 meters. That answer has 2 significant digits. Okay, some new information in this video, so if you had questions, make sure you have those written down so that we can look at that the next time you're in class. We'll practice this some more the next time, and until then, have a nice day. You're all wonderful people. Take care.